Hello everyone. In this presentation, I will introduce our latest research accepted at ICMR 2026, titled Geometry-Guided Depth Correction for Metric Relative Pose Estimation. This work addresses the bottleneck in computer vision, recovering high-fidelity, metric-scale 3D geometry and relative camera poses by correcting the structural inconsistencies inherent in single-view depth estimates. To understand our contribution, we first review the evolution of relative pose estimation. Traditional pipelines rely on extracting and matching 2D key points across images. However, computing the translation vector from purely 2D matches inevitably suffers from scale ambiguity. The current state-of-the-art trend therefore explicitly lifts these 2D pixel matches into 3D space. By incorporating depth information as a structural prior, we transform a 2D matching problem into a 3D alignment task. With powerful models such as DepthPro, monocular depth estimation can now predict metric-scale absolute depths with high visual fidelity. However, a critical bottleneck arises when applied to multi-view geometry. Because these depth maps are generated independently for each view, they lack a consistent absolute scale across different images. Furthermore, they exhibit severe local geometric distortions, particularly around object boundaries and regions with drastic texture variations, leading to systematic drift in 3D space. To address these cross-view scale inconsistencies, current state-of-the-art methods rely on global affine correction. For example, as shown in the left column, correcting monocular depth via least squares fitting of scale and translation still leaves severe local geometric and absolute scale inconsistencies between views. Furthermore, as the right column shows, even advanced methods like MadPose, which corrects stereo depth by jointly optimizing absolute scale, relative scale, and translation components, cannot solve the fundamental issue. This strategy assumes that the depth error distribution is uniform across the entire image. As the discrepancy maps show, this global assumption fails to rectify nonlinear, spatially varying local distortions, limiting its applicability in high-precision metric tasks. This critical limitation motivates the core idea of our paper. We argue that global scale alignment based on affine invariance is fundamentally insufficient. Instead, our framework adopts a geometry-guided depth correction paradigm. By explicitly leveraging cross-image geometric correspondence, our network perceives and corrects nonlinear geometric biases at the local patch level. The resulting discrepancy map on the far right demonstrates significantly smaller errors and stronger local geometric consistency. Here is an overview of our unified perception correction estimation pipeline. Given two overlapping images, we begin with the multi-prior extraction module. Instead of training from scratch, we leverage multiple frozen pre-trained foundation models. We use DepthPro to extract initial metric depths, DynOf2 to provide high-dimensional semantic feature maps, and LOfter to establish semi-dense cross-view pixel matches. These combined priors form a robust foundation for the downstream correction mechanism. To rectify inconsistencies, the extracted features are fed into our depth correction transformer, which alternates between self-attention and windowed cross-attention WCA. Inspired by Swin transformer, we explicitly constrain the cross-attention search space using our matching priors. For a given query coordinate in the source image, we locate its matched pixel in the reference image and define a local spatial window around it. This prevents the network from being distracted by identical but irrelevant regions, enabling it to perceive geometric inconsistencies strictly within corresponding local areas. After capturing contextual geometric information, our module performs local depth residual learning. Instead of computing a single global shift, the network predicts a nonlinear scaling factor, S, for each individual matched patch. We formulate this correction mathematically using an exponential mapping in log space. By setting the scaling constant beta to the natural logarithm of 5, we achieve a dynamic correction range from 0.2 to 5 times the prior depth. This guarantees physically positive depth values while symmetrically balancing the learning gradients for both depth overestimation and underestimation. With the locally corrected depth maps, we lift the 2D pixel correspondence into 3D spatial points using the known camera intrinsic matrix. This converts monocular priors into rigid 3D constraints with absolute scale. Finally, these 3D points are fed into a differentiable geometric solver. Drawing on probabilistic selection paradigms like DSAC, our differentiable RANSAC directly uses the matching confidence scores as weights. This key design allows the pose estimation error to backpropagate and guide the depth residual learning. To train the entire framework end-to-end, we design a joint loss function. It consists of a relative pose loss that applies robust L1 supervision on rotation and translation parameters. However, regression loss alone is prone to geometric drift. We therefore introduce a 3D geometric consistency loss. By using the ground truth pose to transform points, we minimize the explicit spatial deviation. Furthermore, a tan kernel combined with matching weights ensures that large outlier matches do not destabilize the learning of fine-grained local depth residuals. Let us examine the quantitative performance on the challenging ScanNet 1500 dataset. We report the pose area you see at 5, 10, and 20 degree thresholds. Using raw, uncorrected depth pro predictions alongside ELOFTR yields in AUC at 5 degrees of only 3.64%, indicating that monocular nonlinear deformation severely degrade 3D matching. However, integrating our local depth residual learning raises this metric to 33.83%. Notably, our metric scale output, even without global alignment, outperforms state-of-the-art relative methods such as MAST3R, validating that our method recovers true physical geometry. Beyond pose estimation, our framework also serves as an effective depth enhancer. When independently evaluating the absolute geometric consistency of the generated depth maps, our model significantly improves the initial depth pro prior, increasing the delta-1 accuracy by 37.5% to 0.88, and reducing the RMSE by over 30%. The cumulative error distribution chart illustrates this clearly. Under the stringent sub-0.1 meter absolute error threshold, our LDRL correction achieves a valid patch ratio of 0.44, representing a fourfold improvement over the uncorrected baseline. Finally, we evaluated our method on visual localization using the 7 scenes benchmark, a dataset known for textureless walls, motion blur, and repetitive structures. We performed absolute pose regression using only a single, randomly selected reference pair. Despite this strict data constraint, our method outperforms all existing single-pair networks, reducing the average translation error to 0.05 meters. In fact, with only one image pair, our refined geometry achieves metric localization accuracy comparable to or surpassing highly complex multi-pair reference models such as AnchorNet and SNet. Before concluding, let us briefly examine the ablation of our hybrid loss. If we optimize solely on relative pose regression, the network suffers from geometric drift, with translation error stabilizing at 0.12 meters. In contrast, relying only on 3D geometric consistency reduces the error to 0.08 meters, confirming that aligning explicit point clouds guided by match priors is structurally more effective. However, the best performance of 0.06 meters is only achieved through joint optimization of both terms. This confirms that robust multi-view spatial constraints must work in tandem with global task supervision to attain true metric fidelity. In conclusion, our research shifts the paradigm of metric relative pose estimation by transitioning from flawed global affine corrections to fine-grained, geometry-guided depth refinement. By synthesizing pre-trained foundation models, local depth residual learning, and a fully differentiable RANSAC solver, we bridge the gap between single-view approximations and precise multi-view metrology. Looking forward, our architecture lays the groundwork for extending precise spatial perception to large-scale outdoor scenarios and incorporating temporal consistency constraints for video-based localization. Thank you all for your time and attention. Please refer to our manuscript for more details and results.